Unit 6. This is still Learning Target 6A, which is about solving systems of linear equations. So in our last video, we learned about how to solve systems of linear equations using graphing. And in this video and in the next video, we're going to talk about two algebraic approaches to solving a system of linear equations. So by the end of this lesson, you will be able to solve a system of linear equations by using substitution. So how we solve a system using substitution is it really comes down to choices we make. And the first thing we have to do is pick one equation, and in that equation we have to pick one variable to solve for. It doesn't matter which equation we pick, it doesn't matter which variable we solve for, but we get to make this first choice. From there, we want to sub that value into the other equation in place of the variable that we picked in step 1. So as we're going through these kind of how-to steps, let's start looking at our first example. So all of the instructions for this video say solve the following systems by substitution. So in example 1, we have a system here. Remember, a system is two or more equations together. So in this case, two or more linear equations. We have the line y equals 3x, and we also have the line x plus y equals negative 32. So our step 1 here says pick one equation and solve for one variable. What I tend to look for is first, is either of the two equations already solved for in one variable? Meaning, is one of the equations already in the form x equals or y equals? So our goal here is to get an equation in the form of x equals something or y equals something. Well, in this problem, we already have the first equation in the form y equals, and in this case, it says y equals 3x. So step 1 is actually already done for us because we already have one variable that is isolated. What step 2 says is to sub that into the other equation in place of that variable that we picked in step 1. So we're going to substitute in y equals 3x in place of the y value down here in our second equation. So I'm still going to have x plus, and I'm going to have whatever is going to go in place of y equals negative 32. That still all stays the same in the second equation. What is going to change now is that we are substituting in what y equals into the second equation. So because y equals 3x in the first equation, I'm going to substitute in a 3x in place of the y in the second equation. That's what step 2 here is referring to. So we're subbing in y equals 3x in place of y into our second equation. The next thing we want to do from here is we want to solve this equation. So when I get down to this step, I shouldn't have any more y's, and I don't. So my equation is all in terms of x. I can solve this by combining like terms. So we end up with 4x equals negative 32. Then to get x by itself, I can divide through by 4, and x will end up equaling negative 8. So we've now solved the equation in step 2. What we want to do next is sub our answer that we just got, so x equals negative 8, into one of the two equations that we started with. So I'm going to use the first equation, y equals 3x, because we do need to sub it into the opposite equation. And we've already used the bottom equation so far. So as we sub it into y equals 3x, I'm going to sub in negative 8 for x, and I'll get y equals 3 times. We're going to substitute in this negative 8 value for x. So we get y equals 3 times negative 8. From here, we can simplify that. 3 times negative 8 is going to give us negative 24. And that is our value for y. The last part of this says write our final answer as one coordinate pair. So we talked about in the other video how when we have a system of equations, we're looking for a solution for that system, which means we're looking for a coordinate pair that is true for both of the equations. So our final answer here needs to be a coordinate pair, and I want to make sure I write it as the x, so negative 8, comma the y value, which is negative 24. And that right there is going to be our final answer for question 1. So as we can see, we got to make choices in our first example here, so we get to choose what equation we want to work with first and what variable we want to solve for. In example 1, it was kind of nicely laid out for us since we already had an equation that was of the form y equals. So we can see that right there. We already had that y isolated, so I went ahead and substituted that in to begin with. Let's look at our second example. Our second example has the system y minus 7 equals 2x, and negative 4 equals 4x minus 4y. So unlike in example 1, I don't already have an equation that says y equals or x equals. So this is a choice that we now get to make. And it doesn't matter which equation we use, and it does not matter which variable we solve for. We just need to make a decision, pick one of the variables and stick with it. What I tend to look for is I look for a variable that does not have a coefficient next to it, meaning the coefficient is just that invisible 1 there. So what I'm noticing here is that in our first equation, I just have a y with technically a 1 in front of it. On all the other variables, I have a coefficient that does not equal 1. So I'm going to go ahead and solve the first equation for y. And the reason I look out for the variable that doesn't have a coefficient is just because it makes it easier to solve for. It doesn't mean I couldn't pick another variable and solve for it, but I'm looking for the route of least resistance right now. So I'm going to take this first equation and I want to isolate y. So to do that, I'd have to add 7 to the other side, and I'll get 2x plus 7 will equal our y value. So I've now picked one equation and I solve for, in this case, our variable y. What I'm going to do from here is substitute in that y value into the opposite equation. So in place of the y in the second equation here, I'm going to substitute in 2x plus 7. So the negative 4 equals 4x minus 4 is not going to change. That's still part of our second equation here. And I'm going to put big parentheses around it because I want to make sure that the entire piece that I substitute in here for y, the 2x plus 7, that both of those terms are getting multiplied to the negative 4. So as you're solving systems of equations, silly algebraic mistakes like forgetting parentheses or forgetting to distribute, that's the stuff that's going to end up causing you the most trouble. So we want to make sure we're taking it a step at a time and really showing all of our work. Now that we have our new equation just in terms of x, I'm going to go ahead and solve this for x. First thing would be to distribute the negative 4. So I get negative 4 equals 4x minus 8x minus 28. From here, I want to combine like terms. So on the right-hand side, 4x minus 8x will give me negative 4x. I still have the negative 28. I'm going to move the constants to the right side. So if I add 28 to both sides, I'd end up with 24 equals 4x. The last thing I could do is divide through by negative 4, and I would get that x equals negative 6. Or you could write negative 6 equals x. Now we're pretty much almost done with the problem, but the last thing we have to do is do a back substitution in to find our opposite variable. So we've already solved for our x variable. We know that x equals negative 6. So I can start to write out my final answer here because I know that final answer has to be a coordinate pair, and the x will be equal to negative 6, so I'll put that in the x spot. But to find our y variable, I'm going to substitute in negative 6 into the opposite equation. So our first equation that we haven't used since then was y minus 7 equals 2x. And I can substitute in negative 6 in place of the x, since that's what x is equal to. When we do that, we get y minus 7 equals 2 times negative 6. And from here, we can solve for our y. So y minus 7 equals negative 12. When I add 7 to the other side, y is going to be equal to negative 5. So in my final coordinate pair then, I'll have negative 6, comma, negative 5. Going back to these parentheses that we talked about here earlier around the 2x plus 7, notice that if I were to forget those parentheses, I would end up with a different answer for x, which would in turn give me a different answer for y. So little things like parentheses and distributing is going to make a huge difference in these problems. The other thing that's important to remember is, just like we talked about in our last video, if I have an answer, I can always check that answer. So I could check both of these answers by substituting them in and making sure that each equation is holding true. So in example 1, I could take -8, -24 and sub it into the first equation and make sure I get a true statement. And I would do the same thing and sub -8, -24 into the second equation and make sure that it is also going to be a true statement. Remember, to be a solution to a system, it has to be true for both equations. So when you're checking your answers, you want to make sure you're checking it into both equations. All right, let's look at our third example. So our third example here says x plus y equals 3 and -4x plus y equals -2. And we want to solve this system by substitution. So the first thing we have to think about is, well, I need to pick one of the equations and I need to solve for one of the variables. I'm going to go ahead and pick the first equation. Why not? It's the first one listed there. And this time I'm going to solve for x instead, because it does not matter which variable we solve for. So let's see an example where we solve for x instead. I would subtract the y over and I'd get x equals 3 minus y. From here, I can substitute this into the other equation in place of the x. So anywhere I have an x in the other equation, I'm going to substitute in a 3 minus y, since that's what x is equal to. So that's going right in place right there. So I still have this -4. I'm still going to have plus y equals -2, but I want to now substitute in this 3 minus y. 3 minus y. There we go. Now, notice something. I'm missing something that's really key. I need to have these parentheses around here because -4 was multiplied to the entire x, and if x is equal to 3 minus y, then -4 needs to be multiplied to both of those terms. Now that we have an equation all in terms of y, we can go ahead and solve. I'll distribute the -4, and we'll get -12 plus 4y plus y equals -2. We can combine some like terms on the left side and get -12 plus 5y equals -2. We can add the 12 to the other side and get 5y is going to be equal to +10. Let's just make sure we have enough space here. Dividing through by 5 will give us y equals 2 then. Now we're almost done. Our last step is to find our value for x. So I'm going to take this y equals 2 and substitute it into the first equation to solve for our x value. I can also start writing my final answer over here. Since y is equal to 2, then I know that I'll have a 2 in the y spot of my coordinate pair. So I'm going to use the first equation, x plus y equals 3, and I'm going to substitute in 2 for our y value, since that's what y is equal to. When we do that, I'm going to get our x plus 2 equals 3. Solving for x, if I subtract 1 over, I'm going to get that x equals 1. So our final answer here will be 1, 2. So we've now seen in our third example, even if we solve for x, we're still able to work all the way through the problem. And in fact, we could have taken the first equation and solved for y instead. I could have taken the second equation and solved for x or y. It does not matter. We just have to make that choice and continue that choice throughout the rest of the problem. So if you're checking your work with a classmate, if you guys take 2 different approaches, that's okay. Your work is going to be different, but your final coordinate pair answers will be the same. Let's look at example 4. So example 4 says -5x plus y equals -6, and 2x plus 2y equals -12. What do you guys think? We need to pick one of those 2 equations, and we need to pick one of the variables to solve for. What would be the easiest variable to solve for in example 4? So in my opinion, the easiest variable to solve for would be y in the first equation, since the only coefficient in front of it is a 1. I could solve for the x in the first equation or x or y in the second equation. I'm just noticing that it's going to be a little bit less work to solve for the y in the first equation. So I'm going to go ahead and do that. To get y by itself, I'll add 5x to both sides, so I end up with 5x minus 6. My next step here is I want to substitute it into the opposite equation. Why don't you guys pause the video and finish out this example, and then we'll check it together. Okay, let's check this together. So we're substituting in y equals 5x minus 6 in place of the y in the second equation. When that happens, I still have this 2x plus 2 times, make sure you have parentheses here, and then I'll still have the equals negative 12. In place of y is going to go 5x minus 6. Now that I've done my substitution step, I have an equation that's all in terms of x, so I can go ahead and solve for that variable. Distributing the 2, I get 2x plus 10x minus 12. That was a 10, there we go, equals negative 12. I want to combine like terms on the left side, so I'll end up with 12x minus 12 equals negative 12. If I add 12 to both sides, I'll get 12x equals 0 now, which that can happen, that's fine. Divide through by 12, and I'll end up with x equals 0 over 12. What does 0 over 12 reduce down to? 0 over 12 reduces down to be 0. So we've talked about this before. Remember, this is that okay. If I have a 0 on top, 0 divided by a non-zero number is okay. That would give me 0. If you're thinking back to the part that is not okay, would be if I had 0 in the denominator. So if I have the no expression, this would be an answer that is undefined. But we are in the okay case because 0 is in the numerator. So we have our value for x. I'm going to start writing my coordinate pair here, so I get 0, comma, I'll have to figure out what the y value is. To do that, I'm going to take x equals 0 and substitute it into the first equation. So our first equation said negative 5x plus y equals negative 6, and I'm going to substitute in 0 for our x. We will end up then with negative 5 times our 0 plus y equals negative 6. Well, 0 times negative 5 is just going to be 0, so I end up with y equals negative 6 then. That tells me that my final coordinate pair then is going to be 0, comma, negative 6. As a reminder, you can always check these by substituting back the coordinate pair into both equations and making sure it comes out to be a true statement. So if I were to check this, let's go through kind of how we would check it on the last one as a refresher. I'm going to sub in 0 for x, so I get negative 5 times 0 plus negative 6, since that's our y value, and I'm asking myself the question, does that equal negative 6? Well, negative 5 times 0 is 0, plus negative 6, so yep, negative 6 equals negative 6. That tells me that this works in the first equation, but to fully check it, I also need to substitute it into the second equation. So to do that, I'd sub in 0 for x, 2 times 0 plus, I'll sub in negative 6 for y, and I'm asking myself the question, is this equal to negative 12? So I'm putting the question marks there to kind of remind myself that I'm not sure if it's true yet, I'm trying to show if it's true or not. 2 times 0 is going to be 0, 2 times negative 6 does give me a negative 12, and negative 12 does equal itself. So because this 0, 6 made both of those statements true, then yes, indeed, 0, 6 will be our solution to this system. And we can do that checking for any of the examples we did in the video. So if you want the practice, feel free to go back and try that in the first 3 examples to check your work and make sure that solution is correct. And you can always do that on a learning check or a final to make sure that as you're solving these systems, that you're actually getting a correct answer.